Well, but surveying is used.
I asked you for a practical application where this was useful beyond me using it to prove Earth's flat, and you've said knowing the height of Everest. I'm saying when you're climbing up it, and you've got a vague idea by looking at it how bloody massive it is, knowing the exact height measured with elevation changes from a flat Earth perspective, isn't that useful in practical application? Is me hiding the truth if I don't answer it? What, the truth for Everest navigators? You don't seem to be conceding to me. The diagram's depicting a flat Earth, isn't it?
Yes, absolutely.
Okay, and that's how we measure it, isn't it?
Yes.
Okay, that's it. Job's a good one.
See what Jesse's got to say.
Hey, can you hear me?
We can.
Yep, go ahead.
Hooray.
Hey, so it seems that surveyors for hundreds of years, as well as some amateur globers and flat earthers, have found that when measuring angles from one mountaintop to another mountaintop, there's a drop over distance that amounts to around 7 inches per mile squared. How does flat Earth deal with that?
Dave?
Hold on, just before we go on, how did you reference the drop? What was it with respect to? So you know there's an elevation drop by virtue of looking at things. To your perspective, let's just say. To your perspective, they drop at a rate, according to you. So that we know that we've got that measurement, does it have a plane of reference that you can give us the altitude difference from, perhaps? How do you know? What was it referenced with respect to, that drop that you described then? Do you know?
mean like zenith angle? Or elevation angle?
Like with respect to sea level.
Well, no, if you're on one mountaintop shooting an angle to another mountaintop, you reference your level if you're shooting an elevation angle.
We reference our level. Yeah, so we're proving Earth's measured flat and we're referencing level in respect to how high these mountains are. And just so we're all clear about what's going on with the height of the mountains, you appreciate that the height of the mountains is with respect to sea level and therefore a height off a plane. A horizontal plane of reference averaged and known as sea level. So we're going to describe how high these mountains are off a flat Earth and how much a difference in perspective would be asserted to be a difference of a drop over distance with respect to a plane when detailing that elevation change. So it sounds like this question's quite loaded up with flat Earth proofs. How does this question have anything to do with a globe, may I ask?
Well, for example, no, this has to do with a flat Earth. And how do we make our real-world observations fit a flat Earth? For example, I shot an angle to a mountain that was, 5,000 feet taller than the one I was standing on. So, simple trigonometry says it should have been at an upward slope of 0.5 degree. I measured it at a downward slope of 1/10 of a degree. So how in the flat Earth do we predict what the angle to a remote mountain should be?
Just answering. Brian. Yeah. So the angle that you measured required a flat Earth to measure the difference in the angle with respect to a surface level that has established heights of mountains on it. So I just want you to acknowledge that you understand that the heights of these mountains are with respect to a flat Earth, and that the angle you're describing, let's say it's a depression angle with respect to a horizontal plane, that the mountain's heights are referenced to. And it's a depression angle with respect to the ground level that all horizontals will be parallel with. So to describe this difference between eye level and surface level with a depression angle, you will require a flat Earth to measure and describe the angle and give us the heights of the mountains with respect to sea level. That would be, by my count, 3 flat Earth proofs in the form of 3 flat Earth measurements. Do you understand that before we go forward?
Absolutely.
Excellent. So we've proven Earth's measured flat then, with 3 examples that you've given me. What was your question again?
Well, my question is, the problem is, the globers, they come up with a formula. They can tell us, if you're on a mountain this high, and you shoot an angle to a mountain that high, that far, here's the angle you'll get. And they're right. And that's embarrassing because the flat earthers, they can't tell us what angle to expect for a given set of mountain distances and heights. And
Nobody's doing this,
it's high
buddy.
time the flat earthers come up with a formula.
Why would you do
Nobody's
that?
doing this.
Why?
Sorry.
Brian,
Yeah,
is
why
this
would we
not
do
a
this?
Roofy stooge question?
It's
not taken from reality. This is one of Roofy's plant questions.
Yeah, nobody's doing what he's saying. For a start, surveyors don't go up to the top of one mountain and take the elevation of another mountain from the top of that mountain. That is not what surveyors do, number one. Number two, in surveying, right, what they use for all elevation changes is they use the process of rise over run. In rise over run, which is used throughout the whole world for all elevations everywhere, in relation to all other elevations everywhere, rise over run requires that all horizontals, which are all the distances between, are parallel to each other, and all verticals are parallel to each other. That's how surveying deals with elevation changes. Now, at the start of this man added in an 8-inch drop per mile square, 8 inches per mile square drop. Nobody has ever in the history of surveying ever measured that. Ever, anywhere. Nobody measured that. Nobody references it. Now, this other claim where we have this situation where someone's looking at the top of a mountain at another mountain and the other mountain is this from that, blah, blah, blah. I've dealt with that years ago. It's the effect of optical drop. I've shown this, I've demonstrated it, I've explained it, I've shown it in real life. No end. So if you want to make a claim of the opposite, then you've got to show it. Because I can show and demonstrate everything that you're saying, and it all requires a horizontal plane.
These are small, but the ones out there are far away.
Yeah, that's the bit I'd focus on.
Looks like Jesse is sharing his screen. I don't know if you can see it, Nathan.
Well,
if you have any way to view it or not.
with the mountain. Yeah, the two mountains on this
Jesse,
diagram.
go ahead and explain what you're doing.
Yeah, the two mountains on his diagram are on a flat plane.
Right. So we agree that the angle should be the arctangent of the rise over the run, right?
No, I didn't. Brian did, but I'm just you don't seem to be conceding to me. The diagram's depicting a flat Earth, isn't it?
Yes, absolutely.
Okay, and that's how we measure it, isn't it?
Yes.
Okay, that's it. Job's a good one.
So why is what I measure not...
Who cares? Do you not understand that I don't care?
About the truth?
Sorry, the truth is we've measured it flat. And you're asking about an example of how we're going to measure it flat and something that... Sorry, about the truth. Excuse me, does this have a practical application in the real world? How will this be practically applied to someone's life to better it? Give me 3 ways this will better someone's life in practical application. Go.
Well, in 1886, they measured the height of Mount Everest elevation, so I guess that made it better for the people who later tried to climb it because they knew how high it was, they knew how much food to pack, and how much oxygen to bring.
So, and do I strike you as the type of guy about to go up Everest? Is this going to be useful in practical application for me, or is it a very, very narrow and specific field of people that have this single benefit? Okay, fine, I'll accept it. So when we measure the heights of mountains, including Everest, off a flat Earth, proving Earth is measured flat, it's quite useful if you're one of the select few that might decide to go up Everest to know the exact height of the mountain. Not that it has any real bearing on you when you're climbing up it, you're just climbing up it and it is what it is. But knowing the height is useful in practical application. In fact, I decry that this is even useful. When you're climbing up Everest, how the hell is it useful to know how high it is?
Well, but surveying is used for lots of other things.
You don't seem to be answering my question. I asked you for a practical application where this was useful beyond me using it to prove Earth's flat, and you've said knowing the height of Everest. And I'm saying when you're climbing up it, and you've got a vague idea by looking at it how bloody massive it is, knowing the exact height measured with elevation changes from a flat Earth perspective, isn't that useful in practical application? I put it to you. So therefore, I'm getting irritated with you because you're saying that this is me hiding the truth if I don't answer it. What, the truth for bloody Everest navigators? Is that who I'm hiding the truth for, you stupid dick? No, I'm not. How dare you?
Well, Nathan, he did say that they measured the height of Everest from 100 miles away. That would be 100 miles of flat they would need as a horizontal and in parallel to mean sea level to measure that height. Go on, Adam.
Yeah, I'm proving out the question. I'm just sorry, Adam. I'm just going to say I'm proving that the question requires an Earth that's measured flat, which is all I'm here to do. Yeah, accused of withholding truth because I won't answer some stupid trivia question that has no bearing in physical reality, isn't demonstrated to have actually taken place, and has no practical use to anybody ever, but yet I'm withholding the truth according to this guy. It's absolutely infuriating.
Just to reiterate Brian's point, I've just joined the server just to have a look at the images that were being shown. If you look at both of them, the flat Earth calculations, you appear to be taking perspective angles and then applying them orthographically. But again, you're applying it in an orthographic way to a flat baseline. Look at it. If that was in any way a globe calculation, then that baseline of 100 miles needs to curve at 8 inches per mile squared for you to plot it on, for it to be anything to do with the globe. At best, you're resolving for, as Brian described, optical drop. But fundamentally, your mathematical proof for a globe is done on a flat Earth.